Hi, this is Professor Fernandez. In this video, we're going to work through example 417 from Calculus 2 Simplified. This example asks us to verify that the series below are alternating series. We'll talk about that in a minute. And then use the alternating series test to show that they converge. Okay, so quick little review of alternating series. These are series that have one of these two forms, either this form or this form, where b sub n is positive. So the n value, the starting n value, doesn't matter that much, as usual for series. But what does matter is, for example, if we say that they start at 1, that the terms alternate sign, SIGN. So for example, the first term in the series would be minus 1 to the first, b sub 1. Second term would be minus 1 squared, b sub 2, and then so on and so forth. And notice that this is negative b1. Minus 1 squared is positive 1, so plus b2 should be a b2. And then over here, minus 1 cubed, that's negative 1, so minus b3. Because we're requiring that b sub n all be positive, then you can see that this term is negative, this term is positive, this term is negative. They alternate signs as you keep going. Hence, they are alternating series. This one on the right, it's exactly the same as this one, except if I were to multiply this series by negative 1, then the negative 1 here would give me negative 1 times minus 1 to the n. Same base, I add the exponents, and there we go. Minus 1 to the n plus 1, I get that series. So if this is an alternating series, so will this be, and vice versa, right? So the main requirement is that you have a minus 1 to the n or to the n plus 1, multiplying b sub n's that are always positive. When that's the case, then what you're looking at is an alternating series. So let's verify that that's true in these two examples. So this first example, fairly clear to do because we have the minus 1 to the n plus 1 already there. And then we have a divided by n, which we could write as times 1 over n. So this we now see is our b sub n. And then we ask ourselves, is it true that this thing is bigger than 0? Yes, it is, particularly because the n values start at 1 and they go off to infinity. Right? So our series now has this form, minus 1 to the n plus 1 times b sub n, where b sub n is positive. And so check, it's an alternating series. So now I'm going to go back and look at part B. This one's a little less straightforward, which is why it's here as an example. I need to figure out how to turn this into either this or this, right? So how do I figure this out? Well, here are a few things you could do. You could say, hey, I see a minus 2 to the n minus 1 here. And that's the same thing as minus 1 to the n minus 1 times 2 to the n minus 1. How do I know that? Well, remember that if I have a times b raised to some power n, that's a to the n times b to the n. So that's a rule of exponents. So negative 2 is negative 1 times 2. So if I'm looking at minus 2 to the n minus 1, then I'm looking at this product to the n minus 1, which would be minus 1 to the n minus 1 times 2 to the n minus 1. That's what's here. So that's the those are the details on how we get from here to here. Okay, so now I have a little bit, I've made progress, right? I have a minus 1 to some power, but it's in the denominator. So now I have to figure out how to get into the numerator. Here's one way you could do that. You could multiply the denominator by the same thing, and then multiply the numerator by that. In other words, I'm multiplying by 1 in a very special way. You've done this in calculus before, like when you did conjugates, when you were taking limits involving square roots. Okay, so now the numerator becomes this, and the denominator becomes minus 1. I'm in the same base. I'm going to add the exponents. Right? N plus 1 plus n plus 1 is 2n minus 2. N minus 1 plus n minus 1. And then this other term stays along for the ride. Okay, so now I'm looking at the numerator, and I notice that in the numerator, I have negative 1 to the n plus 1. And I just want to study how this changes as n increases, right? What happens to this term? So if n is 1, 2, 3, or 4, right, what do I get? If n is 1, then I have minus 1 to the 0, that's 1. If n is 2, I have minus 1 to the 2 minus 1, that's negative 1. If n is 3, I have minus 1 to the 3 minus 1, that's minus 1 squared, that's positive 1. So notice that I'm getting an alternation here. This is not quite minus 1 to the n, because when n is 1, that would be negative. It's minus 1 to the n plus 1. So in the numerator, I can go back and replace this with n plus 1. They're the same exact outputs that are generated by minus 1 to the n minus 1 and minus 1 to the n plus 1, right, as we showed over here. In the denominator, if I look now at this term, notice what's going on. The numerator is always a positive number. If I take n and I multiply it by 2, that's always an even number, like 2 times 1, 2 times 2, 2 times 7, all even numbers. And then I subtract 2. If I take an even number and I subtract 2, like 10 minus 2, 10 minus 4, I get another even number. And I know that minus 1 raised to an even number, like minus 1 squared, minus 1 to the 4th, is always positive 1. So there's a positive 1 down here. And then 2 to the n minus 1 still remains from what was there. So long story short, we have simplified using lots of rules of exponents and other things our original expression down to this. And so now I go back to my series and I can write the series in this form. I'm going to write minus 1 to the n plus 1 times n over 2 to the n minus 1. And from here we can see that indeed, here's my minus 1 to the n plus 1. And then so this is my b sub n. And I have to ask myself, is this always positive? In order to make this series an alternating series, the answer is yes. Again, n is always positive, starts at 1, goes off to infinity. And then same deal here. These are powers of 2 that are getting bigger. So this is always positive. Okay, so conclusion. Both of these series are alternating series. Perfect. So now I'm going to go off and use the alternating series test to see if they can converge. So here's the alternating series test, theorem 4.13 in the book. It says if I have two alternating series, right, again, b sub n is positive, or any one of these alternating series, will converge when both of the following things are true. So what are the two requirements? Number one, the b sub n's have to go to 0. That's a fairly easy thing to check. It's just the limit. Number two, b sub n plus 1 has to be less than or equal to b sub n. What does this mean? Well, let's think about it. If the b sub n's are equal, then they're just kind of constant. But then maybe at some point it's less than, so it goes down. And then maybe it's equal and then it goes down. So basically, if you graph the b sub n, the values have to be either constant or decreasing, right? So I'm going to just refer to this as decreasing in quotes. The technical term is non-increasing, right? As long as the b sub n terms are not increasing anywhere, right, then that's this criterion. There are a couple of ways to verify this criterion. One of them is called the difference rule. What I'm doing to get this difference rule is I'm going to subtract b sub n, and that is going to give me less than or equal to 0. Another one is called the ratio rule. So I'm going to divide b sub n in here. So b sub n plus 1 over b sub n, less than or equal to 1. Remember, the b sub n's are assumed to be positive. They're not equal to 0. They're not negative. So I can divide by them, and the inequality sign won't change. So subtraction rule and ratio rule. Which one of these you use to verify this number 2 for the theorem really depends on the b sub n expression, right? So some of them will be more amenable to the difference rule, some of them more to the ratio rule. Okay, so back to the example. Remember here we had said that b sub n is 1 over n, and now we look at the first requirement. Is the limit of b sub n equal to 0? Indeed it is, right? We have 1 being divided by a number that's going off to infinity. So that gets closer and closer to 0. Okay, how about this non-increasing / decreasing in quotes requirement? Is this true? Well, we have a few ways we could verify this. Here we could do it directly. We could say, hey, is it true? Yes, it's true from here, because if I take 1 and I divide it by a number that's a little bigger, then I get something smaller, actually, than 1 divided by just that number. For example, 1 over 5 is less than 1 over 4, right? And you can verify this also by saying, okay, if I cross multiply here, I'll get 4 is less than 5. Check. So that's another way to algebraically verify this. We know that n is less than n plus 1. So if I take reciprocals, 1 over n would be larger than 1 over n plus 1. And if I swap the direction here, it would give us what we want. Another way you could verify this, and I do this in the book, is through using a difference rule. So I'm going to look at 1 over n plus 1, that's b sub n, minus b sub n. If I find a common denominator here, I would multiply by n and then multiply here and then keep the sign in the middle, right? And then upstairs in the numerator, I distribute n minus 1 over n plus 1. The n's go away, so I get minus 1 over this. And notice now that this is negative and this is always positive, so this thing is less than 0. So in other words, b sub n plus 1 minus b sub n is less than 0. So that satisfies this difference rule that I talked about a minute ago. So in any of these ways, we definitely show and verify that this is true. So by the alternating series test, that series converges. Great. So now let's talk about the last one. If I go back to a minute or so ago, maybe 2 minutes ago, remember we had written this as minus 1 to the n plus 1 times n over 2 to the n minus 1. That was our bn term. So question, does this bn term tend to 0, right? Is this limit equal to 0? The answer is yes. Now you can do this a variety of ways. If you've learned L'Hopital's rule, you can do that. If you haven't learned L'Hopital's rule, you can use a growth argument. You can say, hey, the numerator is growing linearly, right? Literally grows like y equals x. The denominator is growing exponentially. So denominator is growing exponentially, right? At n equals 1, it's 1, and just grows exponentially. So exponential growth is much, much faster than linear growth. So I have something that's going off to infinity in the numerator, sure, but the denominator is going off to infinity so much faster. And exponentials beat linear functions, really any polynomial. So this limit is indeed 0 by growth argument. So check for that one. Number 2, what if I then go off and try to verify my condition? Is this true? Here, let's try the ratio rule, right? Just to see how that might go. So here, I'm going to look at my b sub n up here. I need to write down b sub n plus 1. So everywhere I see an n, here and here, I'm going to put n plus 1. So n plus 1 over 2, n plus 1 minus 1. And then I'm dividing by b sub n. B sub n is n over 2 to the n minus 1. And we've done this many times before in these videos, in this chapter in the book. Division, right, is multiplication by the reciprocal. So this always ends up simplifying a lot of these calculations in the series portion of a Calculus 2 course. Okay, so here I have n plus 1 minus 1, so just n. And now I do some simplifications here. So n plus 1 divided by n, I'm going to group those together. And then this part over here, I'm going to group that together, 2 to the n minus 1 over 2 to the n. And then I'm going to do some rules of exponents, right? So 2 to the n minus 1 over 2 to the n. Well, 2 to the n minus 1 is 2 to the n times 2 to the negative 1. So when I divide that by 2 to the n, I divide this by 2 to the n. And so these two go away. And so I am left with 2 to the negative 1, which is 1/2. So I'll put this over here times 1/2. So I'm left with n plus 1 over 2n. And question, remember from our ratio rule, I wanted to know if this was less than or equal to 1. So I'm going to look over here and ask myself, is this less than or equal to 1? There are a variety of ways you could answer that question. One of them is you could just divide things out. So n plus 1 over 2n, if I do this v division, so n over 2n, that's 1/2, plus 1 over 2n, here we go. I want to know if this is less than or equal to 1. Well, the n values start at 1 and keep on going. So if I look at this expression, right, as n increases, and I look at the expression itself, what would be the values, right? N is 3, 4, and so on. If n is 1, over here I have 1 plus 1, 1/2 plus 1/2, that's 1. So it's equal to 1, so far so good. Now I start making n bigger. So I'm going to have 1/2 plus 1/4, right? 1/2 plus 1/4, that's 3/4. So now it's getting smaller than 1. And you can see as I make n larger, 1 over 2n gets even smaller than 1/2. And so 1/2 plus that is going to be something smaller than 1. So indeed, I am concluding that this thing is less than or equal to 1. It's equal to 1 when n is 1. For all these other n values, it's actually less than 1. So that tells me that the second requirement here, check for the alternating series test. So indeed, this other series for part B also converges by that test. Okay, that's all I have for you. See you next time.